On Monday, we started reviewing, or we started chapter 2, and we looked at the definitions of and definition and properties of balanced three-phase voltages, right? Also currents as well as impedances. And just to recap, for voltages and currents, three-phase balance would mean that the three phases would have the same magnitude, right? But out of phase by 120 degrees, right? These apply for both voltages and currents. So if you have balanced voltages or balanced currents, it means that they all have the same magnitude. All three have the same magnitude, and they're all 120 degrees apart from one another. And we also learn about the two different sequences, right? If we follow the counterclockwise reference direction, then it could be a BC sequence. This one is showing ACB, but it could also be ACB sequence, right? So either ABC, like this one, ABC sequence, or ACB sequence, such as this one. Oops, such as this one right there, right? And that would imply the phase angles, right? The phase angle relationship between the three would be different, right? Still 120 degrees, but if you have ACB, for example, then the C would be behind A by 120 degrees, but B would be ahead of A by 120 degrees, right? So that will be reflected by the phase angles. And then I mentioned on Monday as well that we're going to restrict ourselves in this class to just balance systems, right? We're not going to deal with unbalanced, just the balanced systems, which means, which actually be good for us, because when it comes to analyzing circuits, then we only need one of the three phases, right? Either you solve for phase A, and then the other two you could solve using the phase angle relationship. Okay. Any questions so far? That's just a quick recap on what we discussed on Monday. Oh, one more thing, because they're balanced, right? Then if you add them up, right, VA plus VB plus VC, it's gonna give you 0, right? Because they're balanced, right? Imagine if you add the three vectors, then of course you're gonna get 0 resultant vector at the end. Now, I almost forgot to also mention that what we did on Monday is that the definitions of balance impedance or balance load would be slightly different from balanced voltages and balanced currents. How is that different? Because for balanced load, yes, the magnitude will be equal, right? Just like balanced voltages and currents. However, this is important. For balanced load, the phase angle will also be equal. See that? So for balanced load, not just the magnitude that are equal, but also phase angle will be equal as well. So there's no 120 degree difference in balanced three-phase load. They all have the same angles. Okay. Any questions so far? Another thing that we reviewed, went over on Monday is the two different three-phase circuit configurations, right? It could be Y connection, it could be delta connection, right? And we learned that for a Y connection, the first property that we learned would be that a Y connection has a common node, such as this one right here. You can clearly see the common node right there, right? And then for delta, right, the main property of delta would be that the three-phase voltages or currents or impedances that would form a closed loop right there, right? And today we're going to learn two more properties of a Y connection, right? We're going to learn about Y connection today, and then the remainder of the circuits we're going to cover on Friday. All right. Any questions so far about what we learned on Monday? But there's actually another thing we learned on Monday. How do you convert from delta to y and y to delta, right? And here I show the long equations, right? The general equations to convert from y to delta, delta to y. But fortunately, fortunately, we are dealing with balance. If it's balanced, that means all the impedances are equal in magnitude, right? If you use R, then all these R values will be the same. And that would reduce this long equation to very simple equation right here, right? So if you want to convert from, let's say, y to delta, all you need to do is multiply each impedance by 3 from y to delta, right? And if, on the other hand, if you would like to convert from delta to y, then you would divide the impedance by 3 from delta to y. Okay. Then since we have three phase connections, right? Two different types of three phase connections, Y connection and delta connection. And we have in a circuit, you have sources and you have loads, right? And loads could be in Y connection, delta connection. Sources could be in Y connection, delta connection. Therefore, there would be 4 different types combinations of three-phase circuits, right? That contains source and loads. You could have Y to Y, meaning the sources are connected in Y and the loads are connected in Y. So therefore you have Y to Y, or Y to delta, delta to Y, and finally delta to delta, right? So today we'll start the first one, Y to Y, and I'm gonna do this really slowly because we're gonna learn many concepts, okay, from Y to Y. And then on Friday, we're gonna go faster with the other 3. Okay. Any questions so far? Okay. If not, let's get started with our first three-phase circuits, right? So please pay attention because we're going to learn quite a few um, definitions or terms that would be important in three-phase circuits. Okay. All right. Okay, here is our first circuit, Y to Y connection. As you can see, the sources are connected in Y and the loads are connected in Y, right? And notice that each of the each of the phases, right? When you're connecting the source to the load, right? There is impedance associated with it, right? So first of all, you see, just focus on one phase. Let's say phase A. That's phase A right here, right? Again, they are connected in Y. So you can see for phase A, right? That's the common node. Common node is lowercase n. For the load side, common node is uppercase n. And look at the way I label these, right? On the source side, I use lowercase. On the load side, I use uppercase. Now, again, if I boxed in the phase A only, you can see that for each phase, you have the source, right? VAN, why VAN? Because we have phase A to N, which is the neutral point. And then the source itself has its own impedance, call it Z of S, source impedance. And then the load has its own impedance for phase A, that's Z of L. And then that's capital letter L. And you can see that the two phases, right, the source and the load is connected by this line right there, right? And that line right there has the impedance called Z line or a ZL or line impedance, right? Lowercase l, right? So 3 impedances. Right? Now, in reality or in practice, of course, this connection from lowercase a to uppercase A, which is from the source to the load, this could be miles and miles away, right? It could be thousands of miles, right? hundreds of miles, tens of miles, it's a transmission line typically, right? And that's why we include this line impedance right there, right, to represent the impedance of the line. So in reality, yes, this connection is going to be long distance, right, connection, right? Yeah, so notice that all three phases, right, the other two phases will be identical to phase A. If you look at phase B, um, where is phase B? Right here, you can see that it also consists of the same three impedances. See that? One source, three impedances. If you look at phase C, same thing, right? Right there, gets crowded, but you can see phase C also has one source and three impedances. Okay, identical. Right? That's the reason why, again, when you are solving the circuit, you only need to solve for just one of the phases, right? Either phase A, phase B, or phase C, just one of them, right? And then the other two, you can use the phase angle relationship, right? Depending on the sequence. Another thing I would like to mention is this. There is actually an extra line. I don't know if you noticed this already. There's an extra line that connects the neutral points, right? The neutral point on the source, the neutral point on the load, they're connected by this line right there, right? And this is called neutral line, neutral conductor. See that? And of course, this is in real world, that's going to be a wire or cable, right? And we can represent the impedance right there, the neutral impedance as Z of N. Okay. Now, keep in mind, even though we have this neutral wire, however, right, if we have a balanced system, right, then what we have is this. First of all, this if somebody asks, why do we need this wire? In real world, we need this wire because in real world we have unbalanced systems, right? So that means if we have unbalanced systems, that means if you add the currents, right, then there's going to be current, non-zero current flowing through this neutral conductor, right? So this neutral conductor allows that the unbalanced current to go back to the source. However, we do have for this class what we'll be dealing with is just going to be balanced systems, right? And as you learn, as I also mentioned, as I mentioned a few times already, in a balanced system, let me use a balanced system. Then if you add them up, you get zero, right? Just like the voltage earlier, right? I showed that VA, VB plus VC has to be equal to zero. The same way with current, IA plus IB plus IC must be equal to 0 amps, right? If it's balanced. So imagine if you have current A going that way, right? Current B going that way, current C going that way. Then at this node by KCL, IA plus IB plus IC, which is IN, right? That's actually equal to IN. Right? If it's balanced, it's going to be equal to 0, right? So IN for balance is equal to 0 amps. Make sense? Now, if it's 0 amps, watch, if it's 0 amps, right, by Ohm's law, right, whatever impedance we have here, by Ohm's law, voltage across that impedance would be 0 volts, right? 0 times whatever ohms gives you 0 volts, right? So therefore, in balanced system, since we have 0 amps on the neutral conductor, therefore, there is 0 volts across the impedance, which means I could ignore this, right? I could just replace this impedance with a short, right? It almost acts like a short, right? Like this. Agree? Because it's 0 volts, right? So voltage across a short is 0 volt. So even though there is impedance, because there is 0 current, therefore it acts like, or we can model this impedance as a short. Does it make sense? If there's a, if you have any questions, let me know. All right. So that's done. Now, again, focus on phase A only. All right, let me erase that. Focus on phase A only. If I erase this again, so I won't get too crowded. I'm going to boxed in phase A, which is right here. Right. Notice that for Y to Y connection, we have the same three impedance, right? The one that I mentioned earlier, source, line, and load. Notice that if it's a Y to Y, look at how they are connected, right? They share the same current. Right? If they share the same current, that means they must be connected in series, right? If they are connected in series, that means I could simplify the circuit, right? I could just lump these three impedances into one single impedance, right? And I just call it ZY. That's what I have right here, right? From here, that ZY is equal to the equivalent impedance of the Y to Y connection for phase A would be equal to Z of S plus Z of L plus Z of L, capital letter, right there. And just call it ZY. And it would be the same for phase B and phase C, right? They're all in series, right? The impedances are all in series. So therefore, I could simplify the circuit into the following circuit right there. Make sense? Right, so now I only have one. So now it's a cleaner circuit, right? Before I have three, now I reduce those three into single impedance right there. Any questions? All right. There's no questions. Then the next thing I would like to go over is definitions or terms. So please pay attention, because yeah, if you don't know what the terms that I'm going to explain, then it's gonna get confusing for the other three circuits. Okay. All right. The first one I want to introduce to you is what we call phase voltage and line voltage. Right. So in three-phase circuit, you may have, we will have what we call line voltage and phase voltage. Okay. So let's look at the definition first. What is the definition of phase voltage? So phase voltage, let me zoom in a little bit here. Right. So phase voltage is the voltage that appears across each phase. Right. So we have phase A, phase B, phase C, right? Right there. Phase A, phase B, phase C. Agree? Now, as I said earlier, phase voltage is the voltage that appears across each phase. So let's look at phase A. Right here is phase A, from here to here. Right. So that's the first phase. I have this source phase voltage, right? And so this is our first phase voltage. Right. Excuse me. Applying the definition of phase voltage, you can see that that's the voltage that appears across phase A, right? And I call this VAN. Why? Because this node is the same as that node, right? Which I call lowercase a. And this node right here is the same as this node, which I call lowercase n. So therefore, phase voltage in this example is VAN, right? Notice the plus and the minus there. VAN. That's the first phase voltage, right? If I go to the load side, right here, the load side, right? I also have phase voltage, right? Which again, by definition, is the voltage that appears across each phase. What is the phase on the load? Right here, from here to here. Right. So that's the phase A of the load, right? And I'm going to call it V, capital letter AN, Why? Well, because that node is the same as that node is the same as that node, right? Again, plus minus this way. Any questions so far? So that's phase voltage. Voltage that appears across each phase. Can you tell me at least one more phase voltage in the circuit? Anybody?
VBN, lowercase bn or cn.
That's correct. Yes. So for example, thank you. If you look at phase B, which is right here, right, we can see that we have another phase voltage, right, which appear across phase B, which is from here to here, right? So the plus is right here, the minus is right there. So I call this VBN lowercase, right? Why? Oh, because that node right here is the same as that node right here is the same as this node, right? So VBN. And by the same token as the one who answered earlier, sorry, I didn't catch the name. You can also have the same phase voltage on C, right? Which would be from here to here, right? So right here is the another phase voltage V lowercase cn, right? Okay, same thing for the load. I have two more. That's from here to here, that's VBN uppercase, and from here to here, that's VCN. Any questions? Hopefully that's clear. No questions? All right. If not, then let me erase this because it's going to get too crowded if I don't erase it. Now, that's phase voltages, right? I have VAN, VBN, VCN, right? That one is relatively easy. Now, the other type of voltage, this could get confusing, it's called line voltage. Now, in practice, in real world, that's what people call it, line voltage. The actual name is actually line to line, right? So the actual name of the voltage is line to line voltage, right? By definition, or following the name, right? Again, it's called line to line voltage. It means that it's the voltage that appears across two lines, right? Now, that's why it's called line to line. If I go back to the three-phase circuit here, right? You can see that source A is connected to load A, right? So source A is connected to load A by a line, right? This is called a line right here, like transmission line, right? So that's called line AA, for example, right? Because this line connects lowercase a to uppercase A, right? And then we can also have another line, which is right here. That's called line B, lowercase, capital, and then capital case, capital letter, B, right? And then another line, line C, lowercase, uppercase C. Okay, so I have three lines in here, right? Actually, I have four. The other one is right here, but again, it's kind of useless because there's 0 amps through it. There's another line, and but we're going to ignore this because it's going to be zero volts anyways. Okay, due to 0 amps through the neutral conductor, as we discussed earlier. So I'm just going to erase that one. Okay. So any questions about this first? So we have three different lines connecting the source to the load, right? Now, let's go back to the definition of line voltage. As the name implies, line to line voltage. It means the voltage that appears across from line to line. Well, let's see how many line to lines we have. First of all, we have this line to line from A to B, right? So from here, I have a line to line voltage that appears from line A lowercase to line B lowercase, or from node A lowercase to node B lowercase, right? This represents the first line AA, and the second one represents the second line BB, right? So I have the the voltage from this line to that line right there. Okay. Good. So let's call that's the first line-to-line voltage, right? And in this case, because the voltage goes from A to B, I call that VAB, right? VAB, right there, right? That's the line that goes from A to B. And I also have another line-to-line voltage that goes from B to C, from here to here, right? From B to C, right there. So that's why I call this this voltage VBC, which means it's the voltage that appears from B to C, right? And then another one that goes from C back to A. See? That voltage is called VCA. So this is VBC, and that's VCA. So the third one is VCA. Okay? Is that clear now? That's why it's called line to line, because it's the voltage that appears across two lines, A to B, B to C, and C to A. Can you give me one example of another line-to-line voltage here from the circuit? Anybody? Besides the three that I've already listed, can you name another one from the circuit?
V capital A capital B.
That's correct. Very good. On the load side, I also have line-to-line voltage, right? From A right there to B right there, right? That's the line-to-line voltage VAB, right? And then, so let me use arrow here. From A to B, like that, right? And then what else? Well, from B to C, right there. B to C. And lastly, from C to A. Okay. What is the reason why I use arrows? Because you can see visually, like, or graphically, that I'm forming a closed loop right there, right? A to B, then the next one must be B to C, and the next one must be C to A. So by if you look at the naming, the names that I use for these voltages, all these voltages create or form a closed loop, right? Again, VAB from here to here, and then from B to C, and then from C to A, right? If you do it this way, that's the correct way of naming, naming, not naming, but of assigning or defining line-to-line voltages for this example, right? So as opposed to doing this is what I'm getting at, right? I could also define the line-to-line voltages on the load side to be the following. So these are the three voltages: VAB, VBC, VAC. See the difference between these two? Between this one and that one? Between the first step right here and the second step right there? The difference is that the last one, for the first step, I call it CA. Look at the subscript. The second one, I use VAC. But the thing is, which can I do both? The answer is no. Right? One of them is wrong. One of them follows the wrong. I hate to use sequence, but it is a sequence, right? This is different from the positive negative sequence. Okay, this is naming sequence: A B B C, and then this one is A C. But if you use this naming sequence A B B C C A, you can clearly see by using the arrows, it forms a closed loop, right? And that's what you need to pay attention to, right? When you come up with the naming with the three line-to-line voltages in a three-phase circuit, make sure the naming that you use are correct. The sequencing of the names that you use are correct. A B B C C A. If you use the second step, if I use blue, for example, right, and I do the arrows again, VAB, that's fine. VAB is from here to here, right? Look at the arrow, that's fine, right? And then the next one is VBC. So the tip of the first arrow should be followed by the beginning of the next arrow, right here, which is VBC, right? So the arrow goes from B to C like that, right? VAB right there, VBC right here. Now look at the last one. The last one is from A to C. So that means the arrow goes from A, start from A, and ends at C like this. You see that? So I'm trying to explain this graphically. And by doing this, you can see that the arrow from A to C is the opposite of the other two arrows, the direction of the other two arrows. It's not being consistent, right? That's how you can tell that, oh, there's something wrong with how I named the last one, right? It should not be VAC. In order to be consistent with the other two, therefore, this last one should be, instead of VAC, should be VCA, right? If I do the opposite, if I do VCA, then this arrow means it goes from C to A, like this. If I do that, then it is consistent, right? It forms the closed loop. Does that make sense? Any question on this? Now, what if I write the set this way? V, A, B. It's still on the load side. V, C, B, V, C, A. Are these the correct three names for the three-phase voltages on the load side, line voltages? Anybody? Would that be a good set of three-phase voltages? Three sets of line, yes, three sets of line voltages?
No.
No, why not? Which one is not good here?
VCB.
VCB, yes. The other two, well, you see the first one is VAB, so just draw an arrow, just like I did earlier. VAB, right? And then VCB, oh, that's going to be from C to B, right? And then VCA, C to A. Oh, yeah. So you can see clearly that the one that is not consistent is this one right there. So that is the CB. So that one is not correct. It's not the correct naming. It's not consistent with the other two voltages. So the correct way would be from B to C. Right? So it's going to be VAB, VBC, VCA. Right? Okay. Again, don't get this confused with the positive sequence, negative sequence. Okay, that's separate. It doesn't matter if it's positive sequence or negative sequence. The three voltages would always be the same. Would always be VAB, VBC, VCA, regardless of whether or not this is positive or negative sequence. Then how can you tell if I have positive sequence, negative sequence? Let's say, okay, I just said that it doesn't matter if you have positive sequence or negative sequence. The right three voltages, line voltages on the load side must follow these names, right? Must follow these names. How can you tell if one set is positive sequence, the other set is negative sequence? Can you answer that question? We learn on Monday. How can you tell? By looking at their what? Anybody? By looking at their phase angle, remember? The difference between positive and negative is their phase angles. If it's positive sequence, then what is the angle between VAB and VBC? VBC would be minus 120 degrees behind VAB, right? So just like this. If this is VAB, then VBC must be over here. If it's a positive sequence, right? And this would be VCA. And so for VCA would be plus 120 degrees. So you look at the angles. If it's a negative sequence, then as you know already, you learned from Monday, then the difference between AB and BC would be plus 120 degrees, right? And from A to C would be minus 120 degrees. So phasor diagram would be as before, except now, if this is VAB, this would be VCA, and that would be VBC. Is that good? Again, the naming should be the same regardless of positive sequence or negative sequence, right? VAB, VBC, VCA. again, the one thing that would differentiate between positive sequence and negative sequence would be the phase angles. Okay, now, if that's clear, or any questions on line-to-line voltages? So I have VAB, VBC, VCA. So not this one, sorry. We have this one, right? VAB, VBC, VCA. Can you tell me another example of line-to-line voltage in this example, besides these three right here? Oh, I already have it right here. Actually, I already mentioned it right there. VAB, VBC, VCA, the lowercase, right? The one on the source side. Sorry, I forgot that I already went over that. So now we have, you can see a total of 6 line-to-line voltages, right? 3 on the source side and 3 on the load side. Okay, the source side is all lowercase. They're all lowercase, VAB, VBC, VCA, and the load side would be uppercase VAB, VBC, VCA. Right? Any questions on this? If not, I'm going to erase this. So that's the difference between phase voltage and line voltage. Another definition that I would like to introduce you today would be currents. Right? Just like voltages, currents also have, in 3 phase, we also have what we call phase current and line current. Right? But before I do that, knowing that now that we've gone over a definition of phase voltage and line voltage, can you tell me with a Y connection, just focus on just look at the source side. If you look at the source side, right, what can you tell me about phase voltage and line voltage on the Y connection? Are they the same or are they different? Here's an example, right? Here's our phase voltage from here to here, right? VAN. And here's our line voltage, VAB. What can you say about the 2 voltages? Are they equal or are they different?
They're non-equal.
They're not equal, right? You can see from this example, you can see clearly that VAN, which is our phase voltage, consists of only one source. See that? Only one source. Whereas VAB, line-to-line voltage, from here to here, you can see that covers 2 sources, this one and that one. So obviously they're going to be different, right? So that's the second property of a Y connection. Okay, sorry, I erased this. That's the second property of the Y connection, is that in Y connection, phase voltage is different from line voltage. Right? What is the first property? Common node. What's the second property? That phase voltage is different from line voltage. Okay. Now, what about currents? Let's look at currents. We also have phase current and line current. How do we define phase current? Well, phase current is defined to be the current that flows within each phase, guys, each phase. Right? So phase current is the current that flows through each phase. That's why the name phase current. Where is our phase here on the source side? That's going to be here, right? That's our phase A. That's our phase B, and here's our phase C. Right? Where is the current? Well, that's the current right here, right? Within each phase. So that's the phase current A right there. Where's the phase current B? It'll be right here. Current C will be right there, right? Okay, so this phase current that flows through each phase. What about line current? Line current would be current that flows through each line. What is line again? As I explained earlier, line is the wire that connects the source to the load, such as this one right here, right? Remember line AA, line BB, line CC, right? So the current that flows through each line, there are actually 4 lines, but this is 0 amps, so I'm going to ignore that again. So if you look at the three lines, AA, for example, that's the first current. I call it IAA. And there's the second current right here. I call it IBB. And the last current right there is ICC, right? So IAA is the current that flows through line A from source A to load A. Right? IBB from source B to load B. And CC would be from source C to load C. Okay. Is that clear, the difference between the two? Okay. So one flows through each line and B flows through each phase. Okay. I'm going to erase this. Okay. Let's look at phase A again. For Y connection, just focus on phase A. What can you tell me about the relationship between phase A current and line A current? How do they relate? Anybody? Is phase A current is line A current? What can you say between phase current and line current in Y connection? Anybody?
Someone in chat said that they would be the same.
Yes. So you can see clearly from this picture that, or this circuit diagram, that for Y connection, thank you. For Y connection, phase current is equal to line current, right? So for Y connection, these are all equal, right? You can see also from phase B, they're equal. Phase C, they're equal. All right. So that's the third property of Y connection, right? So now we have three different properties of Y connection. What is the first one? Can you say it? What's the first property of a Y connection? Anybody?
There's a common node.
As a common node, right? Yeah, please say it, because I'm not checking the chat. What is the second property of Y connection? Right. So these are the three properties of Y connection. Okay. Has a common node. Phase voltage is not equal to line voltage. Phase current is equal to line current for Y connection. Okay. Don't forget this. Now, the next thing is, now we're going to go into math. Right? As you'll see, the math is straightforward. It could be confusing though, but because of the phase angles. But the algebra is just algebra, right? You'll see. The question now is, if you look at the last property here, that's easy, right? Phase is equal to line current. But look at the voltage; they're not equal, right? So how can we relate the two? Right? You can see that phase voltage is right here, but line voltage goes from here to here, right? And notice that line voltage is VAB, right? So VAB is line voltage. That's one example, right? So plus right here, negative right here, right? And you can see that line voltage VAB is equal to these two voltages, right? A VAN plus minus, and VNB, right? VNB plus minus that way. See this? So I can see that VAB is equal to VAN plus VNB. Yes. If you look at this circuit right here. Now notice that VNB is actually the inverse of, not the inverse, sorry, is the negative of VBN. How do I know that? Look at the plus of the VNB. It's actually the negative of VBN. And the negative of VNB is the positive of VBN. So therefore, I could rewrite that equation to be like this. VAB, this is all in the book, okay? Is equal to VAN. I know that VNB is equal to negative of VBN, right? So therefore, if I plug this into here, then I get minus VBN. See that? So now I know from that simple derivation, as I said, math is easy here. VAB is equal to VAN minus VBN, right? You can see now I can relate line-to-line voltage with phase voltages. See that? Now, can you tell me what VBC, if you follow the subscript, line-to-line BC, can you express it in terms of phase voltages? Can you guess what is that equal to? Anybody? Will be equal to? Follow the subscript. See that? VBN minus VCN, right? If you follow the subscript. What about the last one, VCA? Can you guess what is VCA equal to? Anybody?
VCN minus VAN.
Yes. So you can see the reason why I'm showing it this way, so that you can tell easily how to derive or express line-to-line voltages in terms of phase voltages by looking at just the subscript, right? Look at the subscript and you will know right away how to express the equation for phase voltages, line voltages in terms of the phase voltages, right? If I do the capital letter VAB, then I know right away by looking at the subscript, that's going to be VAN minus VBN, right? See that? And that's what I have right here. This derivation right here, that's what I have. Okay. Now notice that if I know VAN, VBN, and VCN, if I know the phase voltages, let's say this is positive sequence, right? That's positive sequence, right? Then I could express VBN in terms of VAN, right? Remember, VAB is equal to VAN minus VBN, right? And at the same time, I know how to express VBN in terms of VAN. Because it is a positive sequence, I know that VBN must be lagging behind by 120 degrees. So if I replace VBN with this right here, then like that, you get this equation right here. And at the end, look at what happens. VAB is equal to VAN times square root of 3 at 30-degree angle, right? So now you can see the relationship between line-to-line voltage and phase voltage. This is only true for positive sequence, right? Look, it turns out to be that for Y-to-Y connection or for Y connections, the line-to-line voltage is larger in magnitude by square root of 3 and is behind by 30 degrees compared to the phase angle, the phase voltage, sorry, the phase voltage. All right, and that's what you see right there. Okay. And you can do the same thing for VBC and VCA, right? VAB in terms of VAN, VBC in terms of VAB, because it is positive sequence. You can see that VBC should be behind VAB by 120 degrees. VCA should be the same as VAB, but ahead by 120 degrees. Okay, if you would like to express line-to-line voltage, VBC in terms of VAB. You could also express line-to-line voltage in terms of phase voltage, right? If it's 30 degrees for VAN, then for VBC should be, if it's positive, should be minus 120 degrees, right? So you go ahead and subtract 120 degrees from 30 degrees. That's going to give you minus 90 degrees. If you want to do VCA, that's going to be plus 120 degrees, following the positive sequence, okay? All right, almost done. That's just the phasor diagram, right? That shows you that line voltage is bigger. And the current, same thing, right? IA line current is equal to phase voltage divided by the impedance, as you can see from here, right? See this VAN right there? That appears across here as well, right? Because there's nothing in between, right? There's nothing in the line. So the same voltage, phase voltage, appears across the load. And so by Ohm's law, current through phase current, which is equal to line current in Y connection, is equal to VAN divided by ZY, right there. Right there. If you know IA by positive sequence, you should know the IB. How? Subtract 120 degrees, right? By positive sequence. And you should also know IC. That's going to be adding 120 degrees, okay? All right. And lastly, before we adjourn, you can also do the same thing. You can derive the same, you can follow the same derivation for negative sequence. Just keep in mind, negative sequence is having different angles, right? B is going to be ahead, C is going to be behind, just like this. And then you can do the same derivations that VAB is equal to VAN minus VBN, and VBN can be expressed in terms of VAN, which is ahead by 120 degrees. And you can see that at the end, if it is a negative sequence, VAB is square root of 3, the same as before, right? The same as positive sequence. The line-to-line voltage is larger by a factor of √3. However, if it's a negative sequence, look at the angles, it's different. It's now minus 30 degrees. In positive sequence, let me write, VAB is equal to square root of 3 at plus 30 degrees VAN, right, for positive sequence. Negative sequence, VAB is equal to square root of 3 minus 30 degrees. That's why, as I said earlier, the math is not that bad, but the angles could be confusing, right? Just be careful with the positive sequence and negative sequence. Right? That'll be it. Let's stop right there.